Hello everyone. So in this video we will look into what the determinant of a matrix represents and what is its geometric interpretation. So before starting with the determinant, we look into three things, and these three different things are how we measure something in a one-dimensional space or two-dimensional space or three-dimensional space. So in case of 1D space, the geometric object is line. So line is always measured in terms of its length. So length is the property which represents a one-dimensional space. Okay. So any change in the one-dimensional space is going to affect the length of the line. Ultimately, the length of the line will be affected because it is the property which represents the one-dimensional space. So for example, if we see this is the line of unit length of length 1, and when I say unit length, that means it can be 1 centimeter, 1 meter, whatever the unit that we have taken. One unit of that is called as unit length. So let's say we have the line of unit length, then any transformation T which is acting on this particular space. So this line is basically a one-dimensional space that we are representing, and a transformation acting on this space and scaling it to make it value 2. So what changed in the transformation is the length of the line. Okay, so one-dimensional space is characterized or measured by its length. In the similar way, a two-dimensional space, example of a two-dimensional space is a plane. So for example, we say XY plane or any two axis planes where the frame of references are chosen by us. In that case, the property or the measurement of this particular two-dimensional space is done by the area. So if someone says us that this is a two-dimensional space and these are the coordinates, so how are we going to measure this particular two-dimensional space? What is the parameter that is used to measure this particular space? And it is the area of that particular space. Now, for example, if we take unit area of this particular plane, and some transformation is applied on this particular vector space, then this particular vector space gets transformed and gives us this particular a transformed vector space. So in this case, the transformation is doing a scale up operation. So it is scaling up the vector space, and scaling up the vector space, and how it is visible to us. It is visible to us by the change in area, and we should better say that change in the unit area value. So in this example, the unit area here is 1, and after the transformation the unit area is now increased to scaled up to 4. In a similar fashion, when we come to three-dimensional space, so for example, the space around us is a three-dimensional space. So how we are going to measure this particular space, and that is done by volume. So any transformation affecting the three-dimensional space is essentially affecting its volume. So if there is an scale up operation, for example, in this case, we have a unit volume of 1, and this transformation T is transforming this particular space. This three-dimensional space is transformed by a transformation matrix, let's say T, and this is what we are getting, the final output. And in this case, uh, we see that the volume is 8. So the transformation is scaling up or expanding the space. So these three measurements of spaces we should keep in mind before going for the understanding of what a determinant is and what it does. So in case of line, it is the length. In case of 2D space, it is the area. And in case of 3D space, it is the volume that is changed. So any transformation happening in one dimension, two dimensional, and three dimensional space will affect the length, area, and volume respectively. Okay, so we, for example, take a two-dimensional space, and in this particular 2D space, we take a vector v, And before going for the vector v, we define our basis as this. So we have taken a basis which contains two vectors, two basis vectors, v1, 1, 0, and v2, which is 0, 1. Now we take a vector v in this particular space, and this vector v has the coordinates 1 and 1. Okay, so we call these coordinates as c1 and c2. And this particular vector v can be represented as a linear combination of the basis v1 and v2 as this, and the factor with which each basis is multiplied with is the coordinate c1 and c2. Okay. Now we take a matrix M. For example, we take a matrix M and we call this matrix as the transformation matrix. We call it a transformation matrix or we do not call it a transformation matrix. If the vector is being multiplied by a matrix, the matrix is going to transform the vector always. Okay. So in this case, what we are seeing is we have a matrix M and this is 2002 and it is a transformation matrix. Now, when the matrix M operates on the vector V that we have taken 1 1, we get a new vector V new, and this V new vector is in this particular example is 2 and 2. Okay, so we see that V new is 2 2, and now we can write it in terms of coordinates and in terms of basis vectors. Okay, so here in this particular diagram, we see that earlier we have the basis vector is v1 and v2 that we have taken for vector v, this vector v, and the vector v is as a combination of v1 and v2 was like this. So c1 was 1 and c2 was 1. After the transformation, this vector is scaled up, and now the new vector is 2 comma 2. Okay, or 2 2. Now there are two different ways to look into this. The first The first way is where we look into the vector without changing the basis. So we keep the basis same as it was earlier. So v1 and v2 are still the basis. And if we look into the transformed vector with respect to this original basis, then we see that the coordinates are scaled up or the coordinates have changed. So the basis remains the same, but the coordinates change. That means the vector elements have changed and they have become 2 2. So earlier it was 1 1, and when the transformation M acted upon this vector 1 1, now we are having 2 2. So this is one way of looking at it, that we keep the basis same and we see that the coordinates of the vector are getting scaled up or scaled down based on the matrix with which is operating on that particular vector. Now the second way to look into this is that the coordinates remains the same, that is the vector elements remains the same. So v1 was the vector, v1 sorry v was the vector and 1 1, and the coordinates still remains the same. So it is still the same c1 and c2, but what has changed now after the transformation is the basis. So the basis has changed, but the coordinates remains the same, the vector coordinates remains the same, it is still 1 1, but this is now represented in a different represented with a different basis. Okay, so v2 represented v new is actually v represented with different bases, and this different basis is obtained by the matrix transformation acting on the previous basis v1 and v2. Okay, so these are the two ways, and the second way is the proper way to look into this. That means the transformation matrix M is actually scaling up the vector space. So now the vector space is scaled up with respect to the current vector space. This we can see by the change in the basis vectors. The basis vectors, the new basis vectors are actually a multiple of the original previous basis vectors, and this shows that the transformation matrix is actually affecting the basis of the vector space. So this we can see here also. Earlier we have the xy plane and v1 v2 were the basis vectors, and 1 1 was the vector represented in using the basis vector v1 and v2. Okay. Now there was a transformation matrix that we have used, and this matrix was 2 0 0 2. Okay. And when this matrix acted on this particular vector v, the new vector that we got is this v new. And here we see that if we represent this particular vector, the new vector, in terms of the transformed basis vectors or the new basis vectors, then the coordinates remains the same. Okay, so the vector basis is now transformed under the operation, the coordinates remains the same, and a linear combination of this gives us the new vector v new, and that is 2 2. So what we see is that the new basis is 2 times scaled uh, version of the previous basis. Okay, now if the space is transformed or not by the operation, and if it is transformed, then by how much value it is transformed, that is actually being given by determinant. So if we look into this particular example, here the unit area is 1. If we take one unit length along the x axis and one unit length along the y axis and form a square, then the unit area is 1 here. And if we do the same in this particular case, then the unit area is actually 4. Now this measurement is done with respect to the previous frame of reference. With respect to this frame of reference, the current frame of reference is 2 times. Okay, so the basis vectors are 2 times. So scaling of the first basis vector v1 is done by 2. The scaling of second basis vector is done by 2. We have the new basis vectors as v1 new and v2 new, and the total scaling in the unit area, the scaling in the unit area is by 4. So what actually the transformation M is doing is it is scaling up the vector space, and the factor by which it scales up the vector space is given by the determinant of the matrix. So M is the transformation matrix which is transforming, and in this case it is scaling up the area, and the factor by which it is scaling is given by the determinant of the matrix M. Now we look into a different case, which is a three-dimensional space, and the property which measures the three-dimensional space is volume. Okay, so volume is the one which is going to measure the three-dimensional space. And for this particular example, we take the basis vectors as this: v1 is 1 0 0, v2 and v3. Okay, now we represent a vector v same as we did in the previous 2D case. We are representing a vector v in the x, y, z. So this is the xy plane and this is the z-axis. So we represent a vector v which is 1 1 1, and we write it in terms of the linear combination of the basis vectors. So here also we get the coordinates c1, c2 and c3, which is 1 1 and 1, that is 1 times v1 and 1 times v2 and 1 times v3 all combined forms the vector v. Okay, now we take the transformation matrix M here as this 2 0 0 0 2 0 0 0 2, and this transformation matrix is acting on the vector v which is 1 1 1. Okay, now this transformation matrix when acts on this particular vector v, it gives us a new vector v new, and this v new is this. Okay, now as we have done in the 2D case, we can look into this new vector in two different ways. In the first way, we say that we keep the basis vector same as it is. Then we see a scaling up operation or a scale up of the coordinates. So now we have new coordinates which are uh, scaled up version of the previous coordinates. So new coordinates is 2, 2 and 2. This is the case where we have not changed the basis. So actually when we do not change the basis and look into the vector v new with respect to the previous basis vectors, then we get an intuitive feeling of how the operation, transformation operation is acting on the vector and whether it is scaling up or scaling down. So in this case, since the coordinates are, the coordinate value is increased by a factor, so here the scaling up operation is happening. And the other way, the more correct way of looking into it is where we say that the coordinates of the vector remains the same, that is c1, c2 and c3, they all being 1. The transformation actually acts on the basis vectors, and it transforms the basis vectors, giving us the new basis vectors in which the vector is being represented. So here earlier V was represented in basis vectors V1 and V2. Now the V will be represented in V1 new, V2 new, and V3 new, a new set of basis vectors. So with respect to this, we see that transformation acting on the basis vectors is actually affecting the volume, is actually affecting the volume of the 3D space. And to be more precise, we say that the unit volume is now scaled up. Unit volume changes under the transformation. So in the first case, when we have the basis vectors v1, v2, and v3, and these basis vectors in case of 3D space were 1, 0, 0, 0, 1, 0, and 0, 0, 1. So in this case, the unit volume was 1 only. And as we apply the transformation matrix M and it acts on the vector v, we get a new vector v, and this is represented with respect to a different basis, a new basis, and these new bases are actually 2 times the previous basis. So we see that the v1 new is 2 times v1, v2 new is 2 times v2, and v3 new is 2 times v3. So what it is, what the transformation has done has scaled up the basis. Since the basis is scaled up, therefore the unit volume is scaled up, and by what factor? The factor by which the unit volume has scaled up is given by the determinant of the transformation matrix. So the determinant of the transformation matrix is 8. And if we look into this particular case where a unit volume is scaled, so this 1 is actually 2 times 1 of the previous value. So better way to look it here only, that the v1 new, 1 unit of v1 new is equals to 2 unit of v1, and 1 unit of v2 new is actually equals to 2 units of v2, and similarly for the v3 also. So this one is essentially is equals to 2 times of 1, equals to 2 times of 1, and this is also equals to 2 times of 1. So what it is doing is that it is changing the area. The scaling in V1 is 2 times, scaling in V2 is 2 times, scaling in V3 is 2 times. So this V1, V2, V3 is what? These are the basis vectors. So net scaling in the unit volume is the scaling of all three bases multiplied, gives us the scaling of the unit area, which is 8. And this factor is also obtained from the determinant of the matrix. So this is what it is. So determinant actually is a measurement, and this is a measurement of what? Determinant is a measurement of how the transformation is actually changing certain property. That change in the property is measured or quantized using the determinant, and in case of 1D space it is the length that is changing under the transformation. In case of 2D space it is the area that is changing under the transformation, and in case of 3D space it is the volume that is undergoing the change during the transformation. And the value or the scale at which it is changing, the value by which it is changing is given by the determinant of the matrix, or better to say determinant of the transformation matrix, which is M in this case. So that's it, what it is. Determinant is actually is transforming the space, and it is scaling up the space, and the value of the determinant gives the value by which the space is scaled. So it can be 1 dimension, 2 dimension, or 3 dimensional space, or even we can go to further dimensions also. So that's it for today. Thank you.